Hello. It's a great pleasure for me to be able to introduce to you at this inaugural lecture, Dr. Keith Devlin. We are very much looking forward to hearing his presentation, which is, can there be a physics of learning? And I know that there's going to be a mathematics in that sentence somewhere within very short time. So let's see where you put that mathematics in there, Keith. My name is Connie Svabo. I am professor at Department of Mathematics and Computer Science, and I am also the director of a Center for Research in Science Education and Communication. And Keith, it's a great pleasure not only to have you here to share your knowledge about mathematics, but also to share your knowledge about outreach and communication, because one of the things that you have been doing all of your working life is actually to work with mathematics as it intersects with society. So how do you communicate mathematics for people who are not necessarily professional mathematicians, but also people who are young learners, middle-aged learners, learners at all ages actually. You have done an amazing amount of work in media, communicating mathematics. You have written 37 books, I think, which is
maybe it is.
Is something like that. Yeah. I have the list. I can actually tell you some of the titles, and I will. So just a couple of them. Some of the recent ones: Finding Fibonacci: The Quest to Rediscover the Forgotten Mathematical Genius Who Changed the World. That's one. The Man of Numbers: Fibonacci's Arithmetic Revolution. Another one. Leonardo and Steve: The Young Genius Who Beat Apple to Market by 800 Years. So these are just the three most recent books that you have written of a trade book kind. You've also written 17 academic books. I haven't counted the journal articles, but I know that there are a lot of them as well. And you have been working with gaming and mathematics. You've been working with talking about mathematics in radio shows. You have been doing MOOC, an online course on mathematics, how to teach mathematics thinking. And that online MOOC has actually been seen, I was just checking this morning, by almost 500,000 people. So 500,000 people have watched you and your course on mathematical thinking. That is super impressive. And I don't think that very many people would actually be able to match you in any of this. And maybe that's also one of the reasons why you are the #1 influential mathematician in the world today. So I think that it's a great honor for all of us, for STU, for our research center, for our department, to be able to welcome you here. And I'm looking forward to hearing your presentation, your lecture, and also to continuing the collaboration with you in the next years. I'm sure that STU will be able to benefit greatly from all of your experience. So please, let's welcome Keith.
Thank you. It's that #1 ranking we have to be careful. I mean, it was nice to have, but it was an algorithm. And that kind of an algorithm would declare Britney Spears one of the most important people in the world. So you take the results of algorithm with a pinch of salt. But if you reach 500,000 students on a MOOC, you're going to have an impact when they start measuring it with an algorithm. Okay, there's the mathematics. So the question is, are we at a stage where we can look at education and various other social sciences in the way we look at physics and chemistry and even medicine these days? So that's what I'm going to be talking about. And it actually has 4 parts. And this is somewhat of a history lesson, or at least a history recount of my own. It starts in the 1980s with fundamental research at Stanford on the nature of information. This is when computers were just beginning to be connected together. The ARPANET was in existence. I used to log on in England, and messages were sent through University College London with a 300 baud modem on my desk. So this is when that was beginning to happen. And a whole group of people at Stanford came together, several hundred actually altogether, maybe a couple of hundreds, put it that way, over the next 2 or 3 years and then longer, to try and develop a theory and to understand what was going to be happening and try to predict what was going to be happening. Then that led in the 1990s to work that I did with a social scientist in London called Duška Rosenberg, a Croatian lady. And we applied the research that had been done at Stanford and elsewhere to industrial problems. She was an applied ethnographer, applied social scientist, a social linguist, also had a PhD in computer science, which she got for political reasons as a lady in a male-dominated discipline. And she was doing application work with industry in the UK, and I collaborated her with 10 years. Of my whole career, it was that collaboration that I'm the most proud of. Mathematicians don't know what it's about, neither do social scientists. We're right in the middle of the two of them, so neither of the groups that we are drawing on really follow what we're doing, but the people that do are the people in the middle. Then in the 2000 era, I applied both of those two predecessor studies after the 9/11 attack, working for the US Department of Defense. And I worked for the Defense Department for about 12 years. They came to me, and in the early 9/11 period, even the most pacifist person, which I was and am, was inspired to try and use what knowledge we have to make sure that kind of thing doesn't happen again. And then from 2015 onwards, applying the work that I did for the Defense Department, well, on the one side, to found a video game company for mathematics education video games, which drew on the research I'd done with those thousands of dollars of US Defense Department funding. But we also applied it, a whole group of us, or small group of us, to neuroscience, human creativity, clinical psychiatry, and then more recently I've been thinking, can we use this technique, this method we've developed, this framework, to try and say something about education? This is my startup point. We all know that useful mathematics can and often is based on a picture that we know is not how really it is. I mean, this is local boy makes good, right? I mean, Denmark, this is the Niels Bohr atom. The atom doesn't look anything like that. But boy, is that a useful way to think about it. In fact, it is the way to think about it. If you think of the atom that way, you can do almost anything until you get to the point where you can't, and then it gets very weird. But that has stood the test of time. It's completely false. In fact, we don't know what the atom looks like. We know it doesn't look like that. But if you think of it that way, it's very useful. There's another one. We have this nice, comforting picture that electricity consists of something traveling along a wire. No, it's not. Nothing's traveling along that wire. It's just sitting there. I mean, some electrons are buzzing around. Actually, electrons do travel along a wire. It takes them about 10 minutes to travel a centimetre. So that's not what electricity is about. But if you think of that, that's the way to think about electricity. You can design things, you can build things. Doesn't matter if it's false, it works. So that's the way we think about it. Same with those. Look at the molecules of life. Organic chemistry. These pictures are very useful. It's the way to think about it. And at the level of physics, we've got the famous Feynman diagram, which tells you about certain interactions at a very fine scale. So we've got these pictures of things that we don't actually understand at all. You know, I mean, we don't know what electricity is, actually. We don't know what any of these things are. But thinking of them in these ways allows us to do things, to develop theories, and to build things. It works. So that's the human being looking at things that we know we don't really understand. This is what motivated my research in the 80s. And I'd started thinking about this in the UK, and nobody else was asking this question. But a group of people at Stanford were, and I very quickly latched onto them, and then they quickly invited me over there because they were trying to bring all the people that were asking that question from around the world. And this was to try to understand what's going on when this world was created, and this world didn't exist in the 1980s. So the first question we asked was, what is information? And the way to answer that, since we're trying to deal with a human phenomenon, information was something people were talking about. It was the information of society, there was information technology. It was a thing in society, it was a social construct that people were using all the time. And the question we had was, can we develop some kind of a framework to understand that kind of thing? So we asked ourselves, what do people mean when they use the word? Well, it turned out that it wasn't a thing at all. That the word first appeared in the English language as far as we could see, and there were a lot of linguists involved in this process at Stanford, and the linguists did some of the research, and they said it appeared in around the 14th century, and it was an adjective to talk about a learned person. Then in the 19th century, it changed phenomenally. It was when we got things like newspapers, mass media of different types, reference books, libraries, all of that stuff in the 19th century. That gave the idea that information was something that you could package into little boxes and things, move it around on trucks. It came in units, it had weight, you could buy it, you could sell it, it became a commodity. And then in the 20th century, it changed with technology as this stuff that you could process. So it went from being discrete items to being a sort of stuff that you could process. But the key thing from the story that I'm trying to tell is this stage. Because at that point, information became a commodity. It had value, people hung on to it, it was shipped around, you paid for it, it had tangible boundaries. You know, a newspaper had a certain size, a book had a certain size. So the conception of information was this commodity that floats around. It's still an abstraction, but it's instantiated in lots of artifacts. But when do you actually need to use the word information in that world? Certainly, in a context like that, you don't need to use the word information to explain what's going on. They're greeting each other, they're talking ideas, they're doing all sorts of things, they're having a conversation. You would only call that transmitting information if it was a spy or something like that. That's not a situation for which you need the concept of information to talk about it. This situation that's coming up now, there's almost no way to talk about that without using the word information. We don't say people are sending electrons along wires, because we know they don't do that anyway. We don't talk about that using the language of physics or anything else. We use it with this invented idea. You talk about information when you're trying to say what's happening, when people are communicating in real time, not necessarily real time, but primarily in real time over space. Then you need something called information. So let's look at the sort of the founding idea. Remember, the notion of information as a commodity came around in the 19th century with things like newspapers. So let's think about a newspaper. You have a journalist. This is an early 20th century journalist, but 19th century journalist like that, working on that thing. That person types something out, it gets printed in a newspaper. The next morning it arrives on someone's breakfast table and they read it. So we've got information being produced, information being stored, and information being acquired. It's been shipped from person to person through physical artifacts. But why do we need to talk about it in terms of information? We've got newspapers, we've got typewriters, we've got people at the breakfast table. Why do we feel we need this notion of information? Well, it's because of this rather mysterious factor. That person began with an idea in his head and put it down on a newspaper. I mean, this is all 20th century metaphors, and women didn't exist in the 20th century. They do now, fortunately, but that was the world that's the world I grew up in. It was a strange world, looking back. Thoughts and ideas come from a head. An idea comes in that person's head. So through reading that artifact that gets passed from one to the other, something has passed from the head of the journalist to the head of the person having breakfast. There's a transmission of this mysterious thing from one to the other. What is it that's been transmitted? We're not going to talk about newspapers because that's just an artifact. We all know the newspaper doesn't have to be that important. Something has to have passed over. But the real thing is what's going on up here. So let's do what scientists do when they don't understand something. Give it a name. All right? We'll do that. Actually, electricity isn't a scientific term, but it doesn't matter. We talk about the electromagnetic field or electromagnetic force, which means we give it a name and then we think we know what we're talking about. And in a sense, we do, because it works. And the method works. And we're talking about an idea that seems strange, but we keep doing it because it works. So we have this thing that we'll call information. So when a newspaper is transmitted physically, information is transmitted along with it. Actually, this is really like the electricity example. Electricity is moving through a sort of information field from one person to another. So the question, if we want to pursue this and develop a scientific framework, is how do we talk about the way a person's actions can produce information, or the way a person can acquire information from reading something or looking at something or whatever? How can we go from people and their thinking to this stuff called information, which lives in social space? It's been passed around from head to head with remarkable accuracy. Unless you're in America, where it's all this misinformation, and so they transfer it around in a different way. But in the days when newspapers had editors and were reliable, what was being shipped from head to head was actually honest-to-goodness information. Well, the answer to that question, how do we describe how information gets from people's heads into social space, was provided around the time, the 1980s, when I joined the Stanford group. I actually joined them in 87 by a philosopher called Fred Dretske, who Stanford hired from Wisconsin, specifically because in a book, he'd come up with a very nice framework. It actually came out of Shannon's work on information theory to do with channel capacity, but he took those ideas and turned it into this very nice framework and says, you've got some kind of a signal, something that potentially can carry information. It does it because of a type, a category that that information fits. So the rest of this talk, I'm going to be using the word type, and just understand it as you would do. You know, in a very general term, it's a way of classifying things. So that was his notion of how you do it. You make the work done. The work to make this precise is going to be done by having a theory of types, which mathematicians and computer scientists and various others have got anyway. So the example would be, it's because there are black clouds. So if you have a signal, the signal is the sky. It's color-coded. So the sky is a signal. If the sky is a certain type, i.e. the type where there are black clouds, then because the sky is of that type, you can conclude that it's likely to rain. Because you know from experience that when you look out of the window and the sky is black, it's probably going to rain. It's just experience. And you're not the only one that knows that. Various creatures do tell. We recognize types in the environment in order to guide our action. So there's a substance here. Okay. So now we've got this picture. We can now formalize it because we've got the notion of types. Instead of having a question mark, we can say it's because it's of a certain type. The situation on the right is of a type that means that thought and idea gets captured on that piece of paper. And at the other end, because of the way that paper is configured, the symbols on that paper, it is of a type that that head at the other end recreates that thing. So it all happens because of typing. It's all about typing. Not that kind of typing. As I was putting this slide together, I realized it was typing and typing. It's actually the typing of typing, but anyway. That's the notion that we were dealing with. We're going to use types because that puts us in the realm of mathematics. The whole game here is to try and bring in concepts that we know in advance can be used in mathematics because they exist in mathematics. It wasn't clear at the time which framework would work. The way I'm going to present it, I'm going to present the successful method we came up with. But there were many others being discussed in the 80s as a way of doing this. The Dretske-based idea turned out to be the one that works. Okay. And then we say, well, what's going on is there has to be some rule, some regulation, some regularity connecting those two types. So we have this thing called a constraint, which is going to be a mapping from types to types. We're now in the realm of mathematics. We've got these things called types. We've got mappings between types. In terms of that example, that's sort of related to that example about, it's a different, related to the example about the black clouds. Let me take this one. Everybody knows, and so do many creatures that live in the wilds, that if you see or smell smoke, there is probably a fire somewhere. In English, we have this phrase, if there's smoke, there's fire. You don't have smoke without fire, they say, which is not true, but it's close. So there is a regularity in the world that when you've got smoke, you can reliably and should conclude that there's probably a fire somewhere. So the constraint links those two types, type of smoke and where there's types of fire. So if you see a situation that you can classify as smoky, without moving, you can assume that that thing over there is what it's like up close. Typically, you look at the thing on the left and you don't go anywhere near there. You run like crazy in the other direction, and so does half the jungle. So these regularities that we're classifying as constraints between types, these are what guides action of living creatures. This is rationality, is acting according to the type of the environment you're in and producing the appropriate reaction, the appropriate response. So we've got a framework that captures at a very general level what people do when they behave rationally. And so we've now got something that mathematicians will easily recognize, because if you throw away all the pictures and leave the arrows, you're going to end up with a very familiar thing from mathematics. Just to summarize, before I go on and do that, let me just summarize. Dretske said that information depends on types. Rational action depends on type recognition. I'm now giving you more of what Dretske did. For a given input stimulus, a rational agent produces an appropriate response. If you see smoke, you run. If you see black clouds, you take the umbrella. That's rational behavior. It's based on type recognition, which we know the brain is superb at doing. Constraints are the behavioral norms or whatever that we're going to formalize in a mathematical theory, and they're going to connect types of input stimuli to types of responses. Okay, picking up now with that, we are now in the realms of algebra. This diagram has been around quite a while. There's a whole branches of mathematics that use this thing. It's appeared in several movies. It was the opening sequence of the movie called It's My Turn with Jill Clayburgh, where she actually spends 3 minutes on screen at the beginning of the movie proving a mathematical theorem called the snake lemma, and she gives the right proof. But the proof was actually scripted by a number theorist at Harvard, so bound to be right, but it's actually kind of a fun sequence. I can recommend that first 5 minutes of the movie and then stop the movie because it's boring, but it's a fun movie. Okay, so now we can look at that picture before in an abstract version. You have some situation, some part of the world, something going on. You can type it according to certain types that you have in your repertoire. You have in your cognitive repertoire, you have constraints that produce different types in response. And then you can draw a conclusion by way of that constraint about the thing on the right. So if your situation is of type S, and you know that type is related to another type R, you can conclude that this other situation, whatever it is, maybe the same situation you're looking at, but more closely, as in the fire example, and then you get information flow going that way. So we've now got, the directions of the arrows is sort of an arbitrary choice. I've drawn the arrows in the direction of sort of agency. You recognize S is of type S, you recognize R is of type S, so that's a sort of an agency thing, information flow. But it's a commutative diagram in mathematical terms. The way you interpret the arrows is part of the application process. And note one thing, because this is going to play a big role later on. This has actually got two domains. That's in the world, and that's in the mind. Okay. As I said, this is remarkably similar to the electric wire example. But it's a very... Incidentally, we had, when we were doing this theory in the early days, we had things called infons, in correspondence of electrons. But, you know, it turns out electrons is a very useful concept, even though it's not true. Infons turned out to be a slightly useful concept, but not really important. The analogies didn't work all the way through. So we've got two domains, mind versus worlds, to be able to talk about this stuff. That project came to an end. We've had a bunch of conferences. I tend to write books, and I wrote 3 of those books. And I'll talk about the 2 on the right in a minute. And there were various other things around, but those were the initial books that came out and the papers and the conferences about that project. So that was good. That went on for about 10 years, and then we finally decided. Then I teamed up with this London-based Croatian ethnographer, sociolinguist, and PhD in computer science as well. And we did a whole bunch of work. We worked for about 10 years on problems from industry, improved productivity in industry. She was an ethnographer. She had masses of complicated data. She came to me at a conference outside Stanford at a Silomar, if you've been there. And she walks up to me after my talk and says, I think you've been doing, she's read some of my stuff. She said, you've got stuff that I can use as an ethnographer. And I said, lady, no, I'm a mathematician. I deal with simple toy examples. You've got bookfuls of data from interviews. There's no way I can handle real data. I need simplified little things. She says, no, you can use it. You can use it. And she kept going, and I eventually gave in. And I spent the next 10 years on this incredible research project. Okay, so this was literally taking real data from industry and producing real results from industry that did improve productivity and safety and so forth and so forth. It proved remarkably successful. I'm not going to go into details, but I will just say briefly, it was a method for using that framework I've just described. We used the framework to analyze the information conveyed by a document or other medium. And we were able to say lots of things. we were able to do post-mortems after things had gone wrong and there'd been misinformation. It was very valuable for doing post-mortems. It provided a way of looking at the situation that brought out where the problems were. And it used the process of mathematical formalization, not because we tried to produce a formalization. You're not going to be able to produce a mathematical formalization of a complex human interaction. But the process of trying to do that, you get an enormous number of insights because it's forcing you to be precise about things you would rather not think about. So it turned out to be a very powerful analytic technique. And the way we developed that framework was because Dushka forced me to read a paper in ethnomethodology, which she said is the paper that gets at the issues we're trying to look at. The paper was called On the Analyzability of Stories by Children. This guy spent a lot of time looking at the way small children write stories and how we understand their stories. And it was an amazing paper because the depth of insight was phenomenal. The guy fortunately died in a motor accident at an early age. He was at UC San Diego, I think it was. Certainly one of the Southern California universities. That was the example. The baby cried, the mummy picked it up. Analyze that sentence, that two-sentence story. The reason that was sort of intriguing is everyone understands that without thinking about it. It's instant. You form a picture, you can see this baby crying, the mother comes over and picks it up, and it's warm and fuzzy, and instant, without any thought. Any native English speaker and people fluent don't have to think about this. This is instant. It's not going on in the neocortex. This is going on deep down in the brain. It's just instant. We understand it instantly. However, what about this one? If we need to we're going to have to answer that question because we need to say, why is that different? The first one is causality. That's explanatory. The baby cries, then the mummy picks it up. Then we explain. That's providing a rationality. The baby cried because the mummy hits it. That's a very different scenario. And we don't have to think about it. If we heard that one first, we'd understand it one way. If we heard that one first, we understand it way. So it's not the sort of syntax in a sense. It's something's going on that's very deep. And the question is, can we say what it is? Now, Sachs had a very detailed analysis in the language of ethnomethodology. We were trying to do it in a mathematical framework because we were trying to develop the framework to do this kind of thing. And as Dushka said, if we can make it work for these simple sentences, which work with small children, then it works for anybody. So we have to explain how that happens. We have to produce a mechanism. And this blew me away. This was Sachs, who said, my reason for having gone through he made a whole bunch of observations. It wasn't videoed, it was too early, so it was transcribed by students. My reason for having gone through the observations I have so far made was to give you some sense right off of the fine power of a culture. These are my boldface. It does not, so to speak, merely fill brains in roughly the same way. It fills them so they are alike in fine detail. The sentences we are considering are, after all, rather minor, and yet all of you, or many of you, heard just what I said you heard, and many of us are quite unacquainted with each other. I am then dealing with something real and something finely powerful. That screamed at me, mathematics is going to work here. If you've got that degree of regularity, fine grain, mathematics is going to plug in there. We've got a place where you can plug mathematics into human interactions and be meaningful. Most of the time it doesn't work. But here we're at a level where it's almost, in fact, when I read Sachs's paper, and I read it many times and talked about it with Dushka, I basically said, this is a mathematics paper written in different language. And that was why it was a really good example. It was the right example to look at because it forced us to look at it in that way. And he'd already done the analysis. We just had to transfer his analysis into our mathematical language. And we ended up writing this paper in 1992. And this was the pitch we made for it. We were taking all of this work in ethnology. The analysis had been done and been discussed by that community. We were just translating it into the mathematical language of types. And people said it wouldn't work, but having read Sachs's observation, that I just gave you that quotation, I knew that it had to work because that was where mathematics does work. Okay, this is actually page 19, and this is where we start to get mathematical in our analysis. Sachs, in his analysis, talked about things called categories and categorization devices, how people categorize things in a social context. These are social concepts for categorization. We don't talk about categories and categorization devices. We talk about types and types of types. There's a potential whole hierarchy, but we only need to go to 2. This is like most applications of mathematics. Linear is good, quadratic is more than you need, and you almost never need to go beyond quadratic. This is the same. Linear gets you set of the way, 1 level of types. 2 levels of types buys you almost everything you need. So this is very familiar to anyone who's done applied mathematics. Most real-world problems can be solved adequately with just second power. You don't need to go high, but you can if you need to. You could iterate that. Okay, so we carried out in that. We took his analysis and just transferred it into, of that simple sentences, transferred it into our languages. For example, he says this: if categories are used to categorize 2 members of the population, you normally hear that if you talk about mothers and babies, then you sort of see the familiarity. But you can also talk about babies as members of society. There's babies, there's toddlers, there's teenagers. Babies can occur in different contexts. And usually when you use the word baby, you have to be aware of the context, and that was part of Sachs's argument. So you take this part of it, let's just blow it up. This is where the type switch goes on. You hear those 2 sentences, the baby cried. You immediately think of a baby as a small creature. It's a category of baby in the categorization device have been at the stage of life. So there you're thinking of babies as entities in the scale of human beings. But the moment you hear the second sentence that mentions the mother, then you switch, without knowing it, to thinking of baby as a member of a family. So you've gone to, now we're talking about families. So that suddenly becomes salient. We actually ended up writing that up, and we did various things. We wrote our book. That example was in our book, followed by many examples in industry. I actually ended up writing a book. A publisher came to me and said, can you write one of these business books you buy at Heathrow Airport? I said, that's kind of fun, I'll do that. So I took our theory and I went through, I applied our framework to air traffic control, major battles in history, and case studies from the Harvard Business Review. And I went through many examples and said, here's how our framework can be used to analyze why that battle was lost, why that airplane crashed, etc., etc. So I spent a lot of time looking at transcripts, doing analysis, and pinpointing what went wrong. Not surprisingly, after this happened, within 6 weeks, I got a phone call from DC to people who'd read that, and they were putting together a huge project to do research initially for the National Security Agency. I didn't get contacted by them. I got contacted by someone at an institute called Viridian Systems, who was a contractor. A contractor to the NSA called me up and said, I've read your book, or these books. We'd like you to join this big team. The government's putting billions of dollars, well, millions anyway, into a major national project to stop 9/11 happening again. That project went on for several years. After that finished, I got another gig with the Navy, who wanted the same sort of thing done for them. And then I got a third one from the Army. So I went through I'd only got my citizenship in 2000. Things happen fast in America. And I'm working for the NSA, the Navy, and the Army. The one with the NSA one was to build a very big system that would help intelligence analysts look through masses of data. Okay, I was a small cog in a very big machine. I was developing what they called context-aware logic. The project that turned out to be more interesting in the long term was for the Navy. They're the ones that operate the drones that sort of fly over the Middle East and various places, taking photographs. And they get lots of data from the drones, too much for people to look at. They wanted some pre-processing of the kind that would be valuable. So we spent a lot of time working to produce technology aids to help people sift through the video from the drones. And the project for the Army was a unit of the Army whose job was to keep people alive, primarily the soldiers, because they're worth about $1 million each if they're on the ground. Not much, actually, in a sense, but that was what they sort of work out, but also to minimize cost. This was to get people doing special operations without loss of life, just kill the minimum number of people. It's dirty work, but at least that one had a good aim. It was to kind of keep people alive. So that was a project that lasted it was only about a 9-month project, but it was still interesting to see how far the framework would work. Okay. This was the one that proved valuable, because this is part 3 of the story. And this is where I teamed up with these people. Ted Goranson started out with a PhD in, actually, he didn't get his PhD, but he finished his work on AI at MIT in the days when that was a big thing. Went off to work for defense contractors and various universities. He was a DARPA manager at some stage. He did a lot of stuff. He was well networked, but he had this background in AI from MIT. Beth Cartier is a creative writer. She's a professor of creative writing at the University of Sydney. And she got pulled in because when we were working on the intelligence project, we wanted on the team a novelist, because novelists understand stories. They know how to tell stories, which means they know how to understand them. Intelligence analysis is telling a story based on the data. You have to take the data and tell the story. You have to reconstruct it from whatever information you've got. She has the tricks to do that. And she'd actually, in her work as a scholar, her academic work was actually looking at ways of describing the mechanisms whereby creative writing works. So she was an unusual person, someone who was a creative writer, but had started thinking about what it means to be a creative writer. So she was on the team. She's now a consultant in Australia for all sorts of companies. My job was to take our framework and analyze the great Christopher Nolan movie, Memento, that came out that year. I spent months, a lot of it on aircraft, traveling between California and Europe, looking at that movie and trying to analyze it using our framework, the framework from there. So that was an application of that to the movie. Didn't work. Well, it didn't work in the sense of it didn't predict the ending before you saw the ending. But Christopher Nolan rigged the game. But if you've seen the movie, it's clear that this is the movie to use as a model if you're trying to understand video, any kind of video data for intelligence analysis. Beth Cartier did what Dushka Rosenberg did. She looked for the most simple stories and said, can I understand Little Red Riding Hood using that framework? And that was the level of complexity that really worked. That was the model to think of. Because Goranson then built a prototype of a system that could be used to analyze it. It was a real-time system where you could interactively look at all the connections that must be going on in order for people to understand stories and do things. Okay, so that was the work we did. And then, the fourth part of the story is 2015. After that project ended, the 3 of us, we delivered the stuff to the Navy. We said, well, we've got something interesting here. How else can we use it? For a while, we looked at whether we could build a tool that Hollywood could use for people on social media to discuss movies, because the assumption was people would rip off movies when they were online, so people would get bootleg copies of movies, so the studios couldn't make money by selling people's entry to the cinemas, but if the studios controlled websites with lots of assets for discussing movies and doing mashups with movies, that's how they could maybe make money. It didn't go that way, but we sort of thought about that. But another thread did go somewhere. And it led to a couple of papers that I never ever thought I'd end up writing. One was a paper in molecular biology about which I know nothing, but I do know about what we wrote. And another one, even more bizarre, I ended up teaming up with a very multidisciplinary team from around the world. We looked at memory, neurobiology, how to treat patients with PTSD, how to write novels, a whole bunch of stuff. And we applied that framework and we collaborated with experts at different domains to try and figure out how our tool would fit into these domains. Let me begin with this one. That is the key diagram. There's going to be another diagram, and this is it. This is the equivalent of the Niels Bohr atom. I'll get to that in a minute. So you're looking at the Niels Bohr atom, not that far away from where Niels Bohr came up with it. And it doesn't look much more complicated than his, okay? I'm going to gradually sort of tell you what's going on. Notice, well, first of all, this was his. He did this because he was providing the Navy with a plan for building a system. This was his level 1 system design for what this system would look like. That was the level where you start writing codes to do things. So that was the beginning of the architecture for the system he was proposing we deliver to the Navy. Or at least we deliver the idea, the Navy would then build it. I have no idea if the Navy built it. I didn't have security clearance. So when the thing was shipped, I lost all control of it. Okay, so that was his way of representing the work. Notice that there are two systems here. There's an L1 system, so we've got two systems that are linked together. This is where we're going to get these two levels of types and types of types. This is where we get the pragmatism, the on-the-fly discussions. We're trying to explain on-the-fly decisions that we're not aware of. So we have a two-level system with various connections. But where did it come from? I mean, that's sort of, I remember when I first saw that, I thought, geez, where do you get that from? And after a while, it dawned on me. It came from here. It was that diagram. That's the L1 system. That's the L2 system. Take that diagram, rotate it counterclockwise 90 degrees, and you get that. And that previous diagram, which shown works, we've been using for 20 years, it works, he's now produced a very rigorous, implementable version of that in the form of a system design, first-level system design. That's where the pragmatic phenomenological, I wish we could have used a shorter word, the pragmatic phenomenological types exist. They're sort of over there. I'll see where over there is in a minute. In terms of the Sachs example, the babies and the mummies are the categories over there. The person dealing with them, the person reading the story, those are the categories that you're aware of. You know you're talking about babies, you know you're talking about mummies. You're not aware of the fact that somewhere in the back of your mind, there are those categories governing what those mean. So we've now teased apart something that seemed integral to our understanding, but now we've got it in two parts. We've separated them out into two domains. So if we look back at that sentence, when it gets to that stage and we make that conclusion, it's because we've gone from there, we've drawn on stuff over here to tell us how to interpret those things. And it's done on the fly. It's done on the fly of necessity, and we do it all the time when we're talking about things and we are not aware of doing it. Okay, so in the case of that example, we're going to apply this in different ways. Once you've got a good tool, you can use it. Those are where, in the case of that kind of example, it's types in the world and types of world types. Categories and categorization devices in Sachs terminology. Types of types in Devlin Rosenberg language. And we can put it in different languages. So now we've got another one. The commutative diagram is the hydrogen atom. This is the atom of all of them. This is the atom with all of the electrons and the neutrons. That's the simplistic one. This has several commutative diagrams embedded in it in the right way. The reason this is powerful is everything fits together in the right way. The reason that's powerful is it fits together in a way that matches all of our observations. So it's the right diagram, it's the level of simplicity to make it possible, but it actually captures the issues we need to use because we can draw on all those previous analyses. So this is useful not just to understand information, but to understand rational action. We can analyze it, we can use it. And that's what we started doing. Once we'd made that realization, we've got to this point, we say that constraints connect types, expertise, and this is Dretske, is the possession of a large number of types. We all know that when we walk into the doctor, and the doctor takes one look at you and says, oh, you've got this, you've got that. Expertise. That's why it takes years to become a doctor, with all those years as an intern, because you're developing, not knowledge, you're developing expertise. You might want to call that knowledge, and I would like it, but we don't. So the question was, can we use this in other domains? That's the question we asked. In other words, and we're going back to 2015, have we got the Niels Bohr atom? Have we got something that's useful, or is it just a toy that will work in a few examples? And that's why we started talking to lots of other experts and saying, can you use this tool? The first one we did, because of the connections we had, was there were lots of cognitive scientists we knew. We can understand the mind in general that way. We have something called the real-world mind, and there's something called, I mean, there's all sorts of words like conscious, or subconscious, all sorts of popular words. They all mean they don't really mean anything until you've got a framework. Well, we've got a framework. All the stuff on here, senses, perception, the stuff that deals with the world, that's sort of part of the real world mind. It's the stuff you're conscious of. And we know where that is. It's in the hippocampus, prefrontal cortex. So that's that part of it. Then there's the rest of the brain, the bulk of the stuff inside, what we call the subconscious, that deals with bodily control, instinctive responses, world models. It's fast. We run simulations. There's almost certainly massive parallelism. So I've got this sort of linear thing over here and this massively parallel thing over here. Maybe even quantum phenomena. There's all sorts of speculations about what's going on in the brain. Nobody knows. Nobody will know. We'll just know better. Molecular psychiatry has a phrase called the default network when they talk about this part of the brain. It's the stuff that's always on, whether you're asleep or not. Okay. And so this is we've now got a framework for understanding how these two things interact. And the key now is understanding how the systems connect. Can we say anything about the systems? Because we're about to enter the world of neuroplasticity and reprogramming the brain, which we know works in some cases, in many cases. Certainly one of the things you can say is there has to be here an evaluator and a filter and a selection. If you've got massive parallelism and your conscious brain just deals with a small number of options, you've got to filter almost everything as that. So part of the process is a massive filter. Okay, with that picture in mind, Cartier, the creative writer, said, I'm going to look at those aspects from the point of view of creative writing, and those are the things that so she's going to look at the connections between the two sides for a creative writer. And she was the first author on that paper. And in that paper, she describes, using that tool that Goranson built, that little analytic tool, she describes how creative writing works using that framework as a basis. This was more interesting. PTSD. I actually knew nothing about it then. I was just working with this guy. I spent the last 3 years looking after someone with PTSD, and without this tool, I would have had no idea what's going on. So it was lucky from my perspective. But Larry Sanford, he's actually at the Eastern Virginia Medical School, and he deals with soldiers, troops coming back from wars in America, and with PTSD. So he was really interested in finding ways for looking for treatments of PTSD, and that's what he works on. That model begins here. PTSD takes place, it's all over here. That's where the damage is done. You've got the trauma-induced causal connections between triggers, That's over here. You have no control of that from your real world. It happens to you. You are a victim of this stuff. Because a trigger comes in, a response comes back, and that's a response. And anyone who's dealt with people with PTSD knows this. And it's relentless, and it takes years to overcome it. The traditional way of treating it is prevent the triggers. Learn how to avoid the triggers. That's kind of crude. Let's look down there. Let's look if we can prevent stuff coming back. Can we prevent stuff coming back? Well, this doesn't tell you how to do it, but it provides you a map on which you can start to think about how to do it. And that's what Stanford was doing. Look at the ways you can develop selectors by programming the brain. There are various techniques and available for sending stuff across from the right to the left that will help to work on that thing. It's not unlike going from the one understanding of a baby to another understanding of a baby and a mother. The brain knows how to do that, you just have to train it to do it. And so there are ways of doing this, and that's now and this is a good way to visualize what's going on. Okay, so even though you've got the trigger, you can prevent it if you work on the bottom. This one interested me. I immediately said, what about mathematical creativity? You know, you work for months and suddenly you have an idea. Well, we know how we do mathematics in sort of a formal way, which is linear reasoning. But we also have this massive parallelism. And that's where the ideas are going to come from. My conjecture is it's all, if not all, almost all, guess and check on a huge scale. And I don't know any other way to come up with the fact that you've thought about something for 3 weeks, it seems impossible, and suddenly the idea jumps into your head just when you're getting out of the bath, or onto a bus in one famous case. It's probably guess and check. Your brain runs massively many possible worlds without you being aware of it. You have a very big filter. Being a mathematician means developing a filter to filter away the 99.9% of stuff that doesn't work before you're even aware of it, presenting you with a half a dozen examples that you can apply a logic filter that you've developed through your education. So that gives you a way of thinking about mathematical creativity. A lot of struggle to set that going. Then the brain starts doing it, and we're all aware of that creative mathematician to do it, and suddenly you get insight and it comes out of the blue because you have no access to that stuff. And I wrote not a paper, but an article at the beginning of this year sort of explaining how I think that's a reasonable hypothesis. These are all conjectures now. Okay, so we've got to this point. Finally, what about education? Well, that would look like this. The goal would be to think of the goal of education as developing types. Instead of filling the brain with facts, we want the brain to develop types. We want to develop expertise, not book knowledge. If you view education that way, and I do view, I've actually always viewed education in that way, so this worked for me. But if you do that, then that's learning, that is application and assessment, and we've actually got that familiar cycle, but we've got more stuff in it. That doesn't tell you very much, except you've got these two things. That's an architecture for digging deeper into what's going on. So my conjecture is if we start thinking of education with that architecture in the back of our mind, just as we do physics with the Niels Bohr atom at the back of our mind, that guides what we do. That atom model works. The circuit diagram works because it's at the back of our mind. Neither of them are true, but they work. I don't care whether this is true. So far it works. So it provides us a way to think about education. And with that, I'm done. It is the first time I've given this talk, so I was about 7 or 8 minutes off in my estimation, but it's the first time.
That's great. Thank you, Keith. And thank you so much for giving us, I guess you could say, almost a background for one of the reasons why it's actually really important to work with mathematics in society, in real-world application, in all sorts of use situations. My interpretation of what you're saying is that one of the reasons for that is because this is where the expertise develops, at least for applied mathematics, correct?
It's not just applied mathematics, it's using the mathematical. The reason I call my MOOC mathematical thinking, it's not taking mathematics off the shelf. It sometimes begins with that. In applied mathematics, you take some mathematics off the shelf, you probably have to adapt it. In the cases I'm looking at, the mathematics off the shelf doesn't get you very far. There was a commutative diagram, doesn't do much. We took it somewhere, we took it to a new level. We have a commutative diagram on steroids. That's new mathematics, and it makes it useful. So it's the old stuff completely revamped. It's not just off-the-shelf applications. But it means you've got to get your hands dirty and talk to the collaborator. Yeah. I had to become a social linguist to do that.
And you became a social linguist. I know that you've also immersed yourself into playing World of Warcraft. You've been
I was a top-level player in World of Warcraft, because how else do you learn how to build video games but play them?
So immersive learning in many, many different ways. Yeah.
I'm a child that just likes to try new things. I mean,
wonderful.
Kind of like, there's the hero. There's the hero.
Great. That's so wonderful. Yeah. Thank you. So let's have some questions from the audience. I can see we have one person over there. Yeah. And I'm going to pass the microphone to...
Thank you very much for a great talk. My name is Christine Ben. I'm a medical doctor and a chair here at DS, and interested in gender perspectives, but also, out of curiosity, interested in psychedelics. And I just think you provided a really nice framework for actually explaining why psychedelics might work against PTSD, where there are some
it does seem like a universal grammar for understanding stuff.
Exactly, yes. By paralyzing the default mode network, psychedelics could actually remove that triggered response. Anyway, my question is about gender, because you talked about how we have rational action, and I'm actually thinking that many places in the world it was males who defined what is rational action, and sometimes even female actions might be seen as irrational in that framework. So I was just wondering, might there be any genetic preponderance or preference for this left side part of your
I'm always very
framework?
suspicious about genetic. I mean, I think it's probably mostly social and upbringing, but I don't know. I mean, one of the interesting things about that project was we followed gender in that team. The creative writer was a woman. The engineering guy was a male MIT type. And I was operating in the middle of this almost like a neutral gender because I was talking to the sociolinguists and the soft stuff and talking to the mathematicians. So I lived in the dangerous middle. You know, they were both yelling at me and I was in the middle. So in our research, we sort of fell into those we didn't choose Beth Cartier because she was a woman. She was the best person for the job. And it just the way. So I don't know. I have no way of knowing whether there's any genetic input. I mean, genes make a difference. Of course they do. Social stuff, we can't do much about that. The point is, as a society, we can do things with social structures, and that's where we have to first think.
Yeah, but I mean, genetics do play a role for your immune system, for your brain, for a lot of different biological aspects. So you could just imagine that it would also have some influence on the way
for those kind of examples, that framework, I can imagine plugging things into that and really finding the nice thing about that diagram is it allows you to look at a particular domain and don't worry about the rest because the diagram will take care of the rest. So you focus on, this is what Larry Sanford does, he just looks at this particular thing and says, oh, well, the machinery will take the rest of it, I'll look at the bit I know. So that would be a way of situating a particular project and then looking at how it would affect things.
Yeah, for instance, the mother and the baby thing, I think, might work differently in the two sexes, for instance. Yeah.
Wouldn't surprise me, wouldn't surprise me. But I'm not an expert. I mean, I'm just a married guy who struggles by.
Okay, we have a question over here. Yes. My name is Gitte Miller-Balslev, and I'm the head of our new National Center of Excellence in Science Education and a part of Connie's team. I have two questions. One from a more innovation research perspective, because I would very much like to know how your work actually relates to maybe Charles Sanders Peirce's work on abduction, because I could maybe phrase it like this. Have you built a mathematical theory to explain abductional human reasoning? Is that what you actually did?
We really try, well, what I think I'm doing is just applying a mathematician's expertise and a way of thinking to that domain. How you translate that to another paradigm or another set of framework, I mean, this is almost like trying to understand one group of people from another. It's fraught with danger, and I'm not sure you could answer the question with any meaningful thing. You could have a conversation, as Dushku and I did all the time. Our research consisted of three or 4 months arguing past each other until we finally understood the other person's perspective, and then we wrote a paper. And we thought, well, that was an easy paper. And then we did the whole thing again. And after about a decade, we couldn't do any more. We were emotionally exhausted, and we stopped collaborating. But it's that kind of question, are you doing this or that? Our methodology was actually not answering that, but arguing over it for a long time. And the arguments led to the insights. It was the process, not the classifications.
Actually, that makes very much sense to me, and it's related to my next question. Because what will be, with your experience, deep experience in interdisciplinary work, what will be your most important lesson for all the scholars here that really want to engage in interdisciplinary work? What should we prioritize?
Empathy.
Empathy.
Oh yeah. You've got to get inside that person's head and see where they're coming from. If you don't do that, it ain't going to work. You've actually got to do that. I'm talking about working at sort of Stanford and things. You're talking to someone with a PhD who's a famous person in their discipline. They've got lots of things. If you think that something that they're doing is silly, you haven't understood it. So you start with that respect and the empathy, and then you spend a lot of time trying to understand what are they doing. When Dushka showed me that example from Sachs, And I looked at it for a while, and we were at a conference in Japan, and we got over the jet lag. We met late one night in a cafe because everybody else was asleep and we were awake. She came from England, I came from California. And we sat there and she said, have you thought about, how far have you got? And I said, Dushka, I'm going to ask you a question, and please take this as a legitimate question. I says, explain to me why that paper is not trivial. And she burst out laughing. She said, you've got to the stage of wondering why you're finding it trivial. I said, yes. Right, now we can start. From a mathematician's perspective, it was trivial. But, that's because mathematicians don't usually look at those problems. Why? Because they can't do anything with them. It was only Sachs's thing about this is fine-grained and repeatable. I said, mathematics has to work here. If it doesn't, it's a sham. We tell people it's about understanding patterns, regular, repeatable patterns. We say mathematics can apply. So I thought, by golly, I've said that in public, I'm going to have to do it. How can we afford empathy? How can we afford empathy? How can we afford not to have empathy? Yeah. Thank you very much. It's all about empathy.
Great. Okay, so we have 2 more questions, and I think we're at the brink of stopping, but I think we're going to allow those.
Because I'm around for another week or so, I'm around, yes.
Everybody, you're welcome to reach out to me, because you are indeed here for a week more.
So,
yes, let's have questions.
And I like beer. Danish, good beer in Denmark, so buy me a beer and we'll chat. Yeah.
So thank you for the interesting talk. So my name is Padilis Periasanaltis. I'm a cognitive scientist by training, and so I've been thinking a lot about categorization. My colleagues do when I go to cognitive science conferences. One thing that plays a lot in many theories of categorization is uncertainty, also coming from Shannon's original theory of information. So one of the things that is dominant there is like probability theory and uncertainty. And I was wondering, does this play into your theory and your conceptualization of communication, and how exactly does uncertainty in communication?
Yeah, that's actually where Dretske started. Dretske literally started with Shannon's definition of probability, and he said, let's take away the numbers and essentially have 2 probabilities, make it digitize it, make it binary. So he took that definition, and by introducing it in terms of types, he says something either has a type or it doesn't have a type. It was based on the whole framework, but it took instead of being the unit interval, it was just 0 and 1. Now, it cashes out in a different way when you develop it. It's a very different framework, but that was the inspiration. It was Shannon, but take away the probability that was part of what he was doing. So it was sort of like saying Shannon needed probability because he was doing it at the level of mathematics, because it was all about building networks and channel capacities. He was using classical mathematics in there. Whereas if you're talking about information is either it's a sort of true or false, it's stuff you need to do. So it's really about what the outcome is for the person. We have to either act or not act one way or another way. And so at the end of the day, the probabilistic notion gets factored out into action or in non-action. You do one thing or the other thing. So as people, he said, cognitive agents, we basically filter out from a probabilistic notion, and we make an instinctive choice, an implicit choice. Now that's the story that you can tell about what he did. In practice, it's if you read Shannon and then you read Dretske, you can see how one came from the other, but it's not a continuous process. He just took that as an inspiration and produced his own framework. And nobody really did anything until we came along. It was just something that philosophers talked about. I mean, Dretske's book was lauded quite a bit. But we were the first ones at Stanford that came in and said, can we operationalize that notion to do something else? Which is what we did.
Thank you.
I'm not sure if that really answers the question, but it's the best I can do on the phone.
Thank you very much for a brilliant talk. My name is Nina Bono-Opdon. You started out very much at the beginning, before the information got going, by people meeting each other and saying, this is not about information because they're doing something else, they're conversing. And so I would like to pick up on that.
Yep.
And ask where, also picking up on Christine's question before, this is all about people being rational agents. But you could, and that's one way of looking at the human being, but another way of looking at the human being is a social being, communicating, creating, meeting, negotiating, without having empathy, lots of other things, and the rationality is just a snapshot that you sort of, or you can argue that You can always put it restructure or recap it as rationality and as irrationality, but maybe that's not what we are all about as humans. So my question to you is, all of what you've just said, is that just a teeny tiny bit of what human beings are, or is it all of it?
I'd say it's all of it for the following reason. What the diagram tells us is almost everything, 99.9%, is on the left, in that huge, massive brain that we're not aware of. So rationality is an illusion that we create when we do something, probably even afterwards. Because what that diagram tells us is it's all on the left. We can get stuff over there with difficulty. Stuff is going on all the time. It evolved to help us survive in various contexts. It does things we have no idea. And we know when it goes wrong with people with PTSD that it's devastating to the conscious mind, all sorts of weird stuff. So if there's anything that comes out of this, it's the message that rationality is largely an illusion, because all of the stuff is on the other side. We have limited ways of affecting it from one system to another. You've got a powerful system over on that side, and this weak little thing that we're aware of, which allows us to do stuff in the world, and we rationalize things, and it seems rational to us, but it would do because it's coming from that side. That brain that we are not aware of, its main job in life is to survive, and it does that by keeping you alive. So it has to control that thing over here. So we feel we need to do things that it knows what it's doing. By the way, the insights I'm talking about now were over the last 3 years dealing with someone with PTSD and trying to figure out what's going on. Stuff is going on there. By the time we know about it, it's almost too late in a sense. So it seems rational, and we think it's rational, but I've also got a daughter who's schizophrenic, and it seems rational to her. When we see things from the L1 system, we're just seeing, it's not even the wall in Plato's cave, it's a line from this complexity. We're just seeing a very weak shadow of everything over there. And that brain that deals with survival simply does not let us know what it's doing. So rationality is an illusion.
Okay, that's going to be the last remark that I'm going to take that with me. So rationality is most certainly an illusion. Thank you, Keith, for your wonderful lecture. Let's give Keith a hand. And Keith